Awesome. Welcome to the seventh week of the internship program. So today we're going to discuss a very fundamental component in AI engineering, which is called RAG. It's a very common term. Most probably you have come across this, and we're going to sort of go into more detail, like what RAG means, which is short for Retrieval Augmented Generation, which is a combination between search and sort of LLMs in general. And it's quite useful, especially this was quite popular when the context windows were quite short, smaller. But I think um, the even though the context windows have been increased, there's also like quite it's quite applicable like even now because like you have these kind of knowledge bases that you need to ingest into your sort of LLM-based tool. So it's quite useful. Even though the theory and things have changed a lot um, from when it was introduced, but I think like you'll see at least parts of RAG within existing systems, and it will be for a while because I think this is a very critical sort of a tool concept, and if you are sort of facing interviews, this is one of those must-know concepts when it comes to engineering. So we'll talk about RAG fundamentals, some techniques around chunking, retrieval, re-ranking, and also like how to evaluate these systems. It's quite critical. Like this is one of those questions some may ask, like, okay, how do you evaluate a RAG system? So let's get into that. So today we'll sort of discuss about what RAG means, the general workflow, like what's the process of a RAG-based system, and some key techniques like embeddings, hybrid search, re-ranking, query expansion, things like that, and go more into detail into evaluation, like how do you measure success of a RAG system, a bit about guardrails as well, and also see how to build a RAG-based system and like how it sort of works. And then takeaways and session for just question and answers. Yeah, let's get into it. Cool. So what is RAG? I think so. RAG stands for Retrieval Augmented Generation. The idea here is that rather than directly sort of sending a query or a sort of message to the LLM, you sort of augment that query with right kind of information so that it has the right kind of context to answer your question. So this is quite useful, especially because you need to make sure that the LLM knows the context. Otherwise, it will start hallucinating. It may sort of get stuff from its own sort of trained data, which is not ideal in your case. So because of that, it's quite important that you sort of make sure that you provide the right the context, and that's where the RAG comes into play. And we'll figure out like how to sort of get the right kind of documentation and sort of fit that in within a RAG-based system so that it can access, the AI can access at runtime this information. So as I mentioned earlier, so the RAG is like the importance of RAG comes into place because hallucination was a problem. So what hallucination means is like the LLM tend to create things out of thin air or generate answers that are not relevant. So to do help with that, so the RAG sort of introduced also like the context window issue. And because of that, you can sort of it's going a bit beyond prompt engineering because prompt engineering is generally prompt would have like bit of context, but it might not have all the information needed for that specific query. So the RAG will help you sort of dynamically change the context based on the query itself, so that it will have the right kind of context for the LLM. You can provide sort of citations and other information, and you get like a much more grounded answer. So that's the theory behind RAG. So if you see a workflow, you understand how it sort of happens. So this is the RAG workflow. So how it happens is that you will, so this is I grab this chart from AWS. So it's like you may see like this is like AWS sort of SageMaker endpoint. So the idea here is that if you look at step by step, um, you'll have sort of a question from a user. Whenever you ask from, let's say, ChatGPT, you ask something. So this is your question, right? So you sort of first send that to your sort of app, and it will sort of first step it will do is like it will sort of convert that to sort of a embedding query, and so it will sort of run against your sort of knowledge database, whether it's a vector database or any kind of a sort of database that you have to store this information and sort of extract that information to get, like, for example, if you ask a question about, let's say, about some sort of a law, let's say in the UK. So you may have like a repository of legal sort of proceedings that happened before, and the RAG, like the vector database, will provide that information as the context, saying these are the relevant sort of legal proceedings for this question. It will send it back. So you'll have that context here, and in your app, so next step it will do is, and before it send it to the LLM, it will sort of embed that enhanced context, which is the relevant information that you got from the vector database. I think we discussed vector databases before, like how do you sort of do cosine similarities and sort of figuring out like what are the closest matching sort of context. So you will have that information here, and that is sent to the LLM, the endpoint, whether it's like OpenAI, whether it's like Claude, doesn't matter. You send this like prompt with that right kind of information, and you get a response back. So that's the general sort of flow. So if you didn't have RAG, let's say if you remove this specific data, sort of a vector database part and the enhanced context, you may not get like a good answer depending on the question. If it's a generic question, that's fine. But if it's very specific to your business, specific to a specific law, if it's especially also quite new and it changes time to time, you might not sort of get this. I mean, the counter to this is like, okay, I may like sort of um, I may add the entire context, like what are the knowledge base within the prompt itself. So that's been tried a lot, and to a certain extent, it may work. So the issue with that is, one, it's going to be quite expensive because you'll be adding a lot of tokens, like for as so the token, the more the token numbers go high, it's going to be expensive for you to like interact with AI. So it's a pricing issue as well. And the other one is like the longer the context, the ability to the LLM to figure out where the right information is, it's going to get low. So there's a needle in the haystack tests that are done. So that means like you try to sort of hide like specific information within a longer context and figure out whether the LLM can sort of extract that information. So if you look at like all the research done on this, like the longer it gets, there's a reduction in extraction of information from these like documents. So because of that, it's got important that you only send the right kind of information. So that's why the RAGs is quite important, and like I feel like it's going to be quite useful, valuable in any kind of a AI-based tool. So that's the reason we're using RAG, not just to get over the sort of the context window issue or the costing issue. So it's actually performance-based decision. Yeah, and like as you can see, there are things around like how you sort of do this. Like, so the RAG workflow is ideally is like, first what you need to do is like ingest documents, like whether it's PDFs, FAQs, APIs. You need to create sort of a data set. And after you get this information, you need to split into chunks. So there are different kinds of chunking algorithms. I'll discuss a few. So the chunking means like how do you sort of break these long documents into pieces and store them in your storage in a way that it makes sense. So one of the easiest ways to like chunk it by length. Let's say 500 tokens. Every 500 tokens, you create another chunk, and then you store them in your vector database, and it can sort of extract that information at runtime. The issue with that is like I'll go into detail later. The issue is like it may sort of break the text abruptly because it's just like based on length. There's no contextual meaning. There's no sort of grounding for that break. It's just like number of tokens, and like different kinds of lines have different kinds of length. Because of that, it may not be the right way, but it's simple enough. Like it's fast, so you can try it as a starting point. And you sort of store this information in your knowledge base with the index of the sort of the embedding sort of vector, and based on that, you can sort of retrieve this information at runtime. You can use something like FIS, which is a local sort of vector database. You can use PG Vector, which is for Postgres vector database. Pinecone, we looked into that earlier, which is a vector database as a service, and you can sort of host your data in the cloud and sort of interact with it. So vector databases are quite important here. And at runtime, as I told you now, you basically query this and get the right information, and sort of enhance, augment the query with that context and send it to the LLM and get the results back. So that's how the general RAG workflow works. There's much more nuance to this and more complex techniques, but I think on a, if somebody asks you to explain RAG, this is how it works. So it's quite useful to understand this. So as I said earlier, so the key building blocks like of RAG, chunking, like how do you sort of split the the your knowledge base before you store that in the database. So how do you sort of break that in? That's quite critical because these are text, like long documents, ideally. It could be like even like multimodal. So how do you sort of break it down in a sensible way? So that's one angle. And embeddings, like how do you sort of create embeddings out of these data sets, the text, the multimodal concept, like how do you sort of in a meaningful way, how do you sort of create embedding? So there are always trade-off, like more precise you're going to be, it's going to be slow to retrieve because like you need to do quite a lot of matches, and also maybe storage point of view to be too much as well. So there are trade-offs that you need to understand when you create embeddings and the vector database as well, right? So how do you, which one do you pick? Do you pick like a local one? Do you pick something open source model? Do you pick something already has like service-based solution, like whether it's with Google, whether it's with Pinecone, etc. So there's a decision there. And also, like after you build that, how do you improve on this? So there are things around re-ranking, which comes from general um, sort of information retrieval or search literature, where how do you re-rank certain information so that you get the right kind of information. So for example, if you look at Google search, they do re-rank. They have a re-ranking algorithm to make sure that the information that matches a specific query, it is has the highest relevance. So because of that, re-ranking algorithms are quite important. So we use these within RAG so that we can improve the data extraction step so that it has the right kind of information at the runtime. Query expansion, which is like whenever you ask a question, like your query, you sort of expand it into to have much more context, much more meaning. So because of that, the LLM would understand much better. And also guardrails, like you make sure that we evaluate the queries that the users ask to check if it has any sort of ill intention, or it could be like something that you can't answer. So things like that. So adding guardrails as well is quite important for RAG solutions. It needs to be added at input level, also at output level. So you need to have checks at both places generally. Um, so the next thing is like looking into chunking strategies. So which is I think the most critical part, and I'll sort of explain some basic chunking strategies. And I'll also go into like this really good article from VV8, which is I think VV8 is a vector database. Their primary angle is that. So they provide vector databases and consultancy around that, but their sort of content around this is quite good. There's really nice uh, graphs, animations, so it's very easy to learn. So they do a really good job sort of creating this information for us to learn the fundamental as well. So here I'm sort of highlighting three types of chunking strategies. The first one is like fixed chunks, which is like based on you. If you get a document, you break it down in like fixed lengths. So there's no theory behind it. You define the number of size of the chunk and you break it down. And it's much faster because it's predefined. There's nothing from operational point of view at runtime. Just break it down and just store that. So much faster. It's fast to extract as well. Other one is like a header aware. So the generally what it means is like uh, if you break it down, it's based on the size. It may miss some of the meaning for that specific text chunk. So to get over that, either you sort of append like a summary of the document, or you just append like previous part or the next part in a way, so that it has some context for that specific chunk on its own. Otherwise, it's very hard to sort of extract that if you use like a semantic based extraction. And the third one is like semantic based chunking. The idea here is that you sort of like break the sections by its meaning, like by semantic meaning. So the first section is like something about the introduction. Second section is about like a specific, let's say, second paragraph. Like likewise, you break it down in a much more meaningful way using semantics. Like you use like some sort of LLM tool here, like a smaller model could be, or even like a proprietary model, and use that to sort of break it down. So in that way, your chunks would have much more meaning, and I think accuracy was quite good, but there's a bit of a initial loading time because you have to like chunk everything and store that with this logic. And if you add something new, you have to do the same. So there's a bit of a cost and time trade-off, but at the initial speed. But at runtime, I think this is something really good. It's quite useful. Um, so I want to like show this document as well. It's quite nice. On the best internet today. Okay. So this is the article I want to show you. So this is from VV8. Do check them out. So they go into detail about chunking, how do you sort of optimize retrieval and preserving context for generation. So there's a lot more information. Do read it separately, but I don't like go into these chunking techniques. Um, so there are like on a high level, there are like two types of chunking. There's pre-chunking and post-chunking. Um, so so the pre-chunking it's sort of like as it is like so you just break it down sort of to smaller sections before you sort of run it through embedding model. So that's what you do with pre-chunking. So post-chunking is generally happening. You run the document through the embedding model first, and you chunk at query time only. So you have the so embedded sort of content before like do chunking. So it's a high level sort of distinction for these like two types of chunking methods when it comes to where you chunk. Um, so so as it says, like however it introduces latency on first access and requires additional infrastructure decision. So as I said, there are like pros and cons for each method. So depending on your use case, you may not need like sort of it's fine to have like initial latency. So as you go, if you need accuracy, you might need to push something like this. So depending on the use case, you make a choice. And then like after this high level sort of distinction where you sort of place a chunking, you have these like chunking methods, right? So the one is like the fixed size chunking we discuss. There's recursive chunking, which sort of like there's a really nice sort of diagram here. So define prioritize list of common separators, paragraphs, sentences, words, and then like split the text using the highest level separator, which its chunks are too big, split again using next separator. So you define like how you want to sort of define the hierarchy of like this recursive chunking. So based on that, it starts sort of breaking it down. And so that's one way to do it. And the other one is so documents based chunking. So if the document has like a specific structure to it, like the headings, subheadings, paragraphs, you use that specific structure so that you store that information that way. So that's one way of doing it. The high level simple chunking strategies, and there's also advanced chunking strategies, which is the first one we discussed, the semantic based context aware chunking. So it sort of break it down by meaning. So you have different sections. So until you figure out, okay, these separate sections has distinctive meaning, and you do this process iteratively a bit until you sort of figure out, okay, these are like very distinct sections, and then you can store this information. So this LLM-based chunking, so you run the text to LLM, and ask it to, okay, generate these kind of like specific sections. I think agentic chunking is quite interesting. So the idea here is like, so you run it by another agent. So so there's also like, let me see, there's a bit more introduction here. So So agentic chunking takes a concept of LLM-based chunking one step further. Um, so it sort of like dynamically sort of let an agent to decide like what's the best way to sort of chunk. So you have functions defined for fixed size chunking, documents-based chunking, semantic chunking, but at runtime the agent will sort of decide, okay, this for PDF, I'll use this kind of method, and for HTML, I'll use a separate method. So you let the agent sort of decide, and you have sort of these optimized chunks and use that to sort of store that information. Likewise, there's quite a few more. Like some of them I haven't used either, so I highly recommend that you read these, like depending on the use case, because so things like semantic chunking, LLM-based chunking, agentic chunking, those are some of the mostly common used ones I've seen. But there are like other methods. It's quite interesting document to read out. So it sort of goes into detail like how different sort of chunking algorithms help. And you have to tweak a bit more, like when you have this in production, to make sure that you pick the right chunking strategy or the combination of chunking strategies depending on your use case. So we also talk about like, okay, a summary of like chunking methods, how it works, complexities, when to use. So some good examples as well. So these are really helpful, detailed sort of chart for you to sort of spend some time when you're building RAG system, especially deciding on the RAG sort of selection. So yeah, this is what I want to show quickly. Do check it out, and I highly recommend that. Yeah, I'm happy to take some questions before I move into the next section. If there are any. All good. Yeah. So we can move to the next section. What's the name?
Like parent chunking.
Parent chunking. You mean parent? P-R-E-N-T? Yeah. It's not. I think like, do you remember the meaning of that at least? Like, yeah, I think like what you sort of like mean something like this. I've used this long time back. So remember like this is one of the first sort of concepts that sort of came for chunking. So you break it down like on a high level, and then so you have sort of like, let's say, document chapter one, chapter two, chapter three. Chapter one is like one of the parent chunks, and then within that chunk you break it down. So I think like this helps you to like have some level of granularity. So if you're gonna go like to very specific information, you can use a child chunks embeddings. And if you need like on a high level, so I'll look into this a bit more. I remember like using in one of the projects. But the idea here is like you have like, so the child chunk would be, um, like will belong to a parent chunk. So based on that, you either can be used to extract the context, like sort of the meaning of that sort of child chunk if it doesn't have like some sort of a meaning. And so based on that, you can extract the right kind of information. So as you say, like for each context, precise retrieval if you need. So yeah, I mean it's one of the methods like, so there are quite a few ways people do these things. Like, so we had to see like what's the good use case for this, and there might be very specific use cases for a parent and child chunking sort of based problem. But yeah, I mean, good question. But yeah, cool. Yeah, awesome. Let's see what's next. Yeah, so the next step is like around retrieval, right? So the idea here, if we sort of go back to the initial sort of chart I showed here, so you sort of first store this information in the database, and then the second question is like, how do you retrieve this information? Like, so how do you find the right kind of chunks so that you can embed, enhance the context? So that's where the retrieval comes into play. This is like the normal sort of computer science sort of retrieval concept, right? You may use dense vectors here means like you use like cosine similarity to figure out like what are the most similar sort of pieces of information that is relevant for this query, and you sort of extract that. You can use something like BM25 algorithm, like using keyword search to figure out, okay, if there are the most important keywords in these chunks, and then sort of try to get them out. Or you can make a sort of combined sort of hybrid approach. So combines dense and BM25 to have like sort of a weighted average and get a score. Based on that, you can sort of extract that. I think, let me see if there's a, there are quite a few other methods as well, but on a high level, like we can sort of like look into these as ways that we can use to extract information from our vector database at runtime, so that you'll have that information needed for the query. Um, see, um, and I think like best way to show this is like try to like show it with some examples. So before I go into this, I want to like show like a quick demo I have done. Let me see if I can load this. Um, so in this article, like I'm gonna try and show like how you would um do the injection, retrieval, and how do you can do that at runtime, how it works, right? So I've created like three sections here. One is for like injection, which is like you sort of load a specific set of data and load that into your database. And how do you do the splitting, etc. On a high level, so the idea here is like so if you ask a question, let's say, explain to me um, like Python. Like, so if you ask ChatGPT, it will give a good answer, like what Python means. But generally, if your company has very specific documents that you want to be provide at runtime for questions, I think this is where comes quite handy. So to show this like this works, I've created like this fake documents. So I've created like this Python document which has called Aquaflow. I think there's nothing like Aquaflow. And so biotech flow industries. So there are like some fake documents with fake names I've created. So this is relevant for these specific companies, etc. So this information is not there. So generally, if you ask the same question from, let's say, like ChatGPT, it is not able to answer this question because those are not there. And so that's the general premise. Let me see if this is running. Let me see. Let it run, but I'll sort of go to the code for now. So the first step is ingestion, right? So ingestion, what I mean by is that you try to sort of like, um, so we have sort of class that does this kind of ingestion. So the steps for this is like, if we go to ingestion, the first thing is like you load the documents, like which is here, basic like loading function, and then you split them into chunks, right? So if you go to split the chunks method, what here we do here is like we sort of like break it down by sort of number of tokens. Like, so you load each document and you sort of like chunk them, break it down into sections, and create like array of list of chunks, and you sort of provide that back. So that's the first step. And next step is like you generate embeddings, right? So you have a set of documents and you call the embeddings method, which is to convert. So embeddings are simply numbers, like multidimensional numbers, like array of numbers. For each text chunk, you'll have this long list of like numbers. And so what this does is like you use the text embedding tree small model and sort of create embeddings for that. And this will extract that embedding and you sort of append this values for this embeddings array. So we're gonna like use the index itself, like the index of the array as the reference point. We are not going to sort of create other set of indexes to track. So if you look at like you take the zeroth index of the embeddings array and the zeroth index of the documents array, you have like the same like element. One is the document itself, other one is the embeddings. And so you create embeddings, and then you create the vector database. In our case, we are using files in here, and we pass these embeddings and ask it, okay, create me a vector database with these embeddings, so that I can sort of extract this information at runtime. So it will create this FICE database. So FICE is an open source vector database created by Meta for their sort of work. So it's quite good actually. It's quite old though. It's like probably 6, 7 years old, but it's quite useful because it's stress tested within their sort of use cases. So it's quite good, and it's performance like efficient, like to run locally as well. So you create that. So this is the first step, right? So you sort of get the documents, split them into chunks, generate embeddings, and then sort of store that information in a vector database. You can make a decision to use a Pinecone or any other vector database, but in our case, you're using this local sort of method. So that's the first step. So the second one is like, so you need to sort of retrieve data. So at runtime, if you ask a question, so I will might be able to show the demo now. It says it's running. Let's see. Yeah, so this is like a just a front end, like a Streamlit application. Um, so what it does is like, so if you ask like, I mean, let's try to ask to what is Python? What is Python? See. So so we can control the number of chunks that we want to extract, and we ask this question. Um, so okay, so priority considerations contain information about what Python is, therefore so it can't sort of answer like, because this in these sort of what I've extracted, there's nothing related to Python. So what I'm going to do is like I'm going to ask about Aquaflow. So Aquaflow, there's nothing like that. So I'm going to ask like, what is Aquaflow? So it sort of generate this question. So I'm going to show you first like, so what if I ask this from ChatGPT? What is Aquaflow? If you try to find something, so something, there's something called dietary supplement, like just all kind of stuff, right? So water cooker, there's nothing related to Python. So where this pulls this information regarding Python based is from our sort of document that we created, right? If you look at the documents, you'll see something here, something called Aquaflow. So this is runtime, it's your company information, like whatever the contextual information that you have. And so here you can see there are three sort of chunks extracted. So in our case, like, yeah, so you have this document which is has the highest sort of similarity score, zero point 0.7 out of 1. And this one has 0.31, so it's not quite good, and it picks the top one, and likewise. So if you increase this, you get more sort of context extracted, and you get like this kind of very contextual answer. So that's the power of RAG, right? So you can have this kind of documents at runtime, and you don't have to define it like for these questions use this. So at runtime, with the power of vector databases and semantic search, you can find the right information, like right set of context, and get these kind of answers. So this is like the simplest form of RAG that you can build. There's much more nuanced, complex system that you can build. This is what I want to quickly show. Then we can go into code a bit more. So so this is the retrieval step, right? So the retrieval step. Um, so the So you set up like a retrieval system. So you get the documents and sort of ingest the documents, and you do that step. And so the next step is like, given, so if you asked it to retrieve, so this is the first step, like given a query, how do you sort of pick the most recent relevant chunks, right? So from application side, first thing you need to do is like, if I go back to this one, I think this is where it's happening. So yeah, yeah. So from front end point of view, so the retrieval step here is like, you have a query, and So this is the question that you may ask, and you sort of use the get query embeddings here, and it will sort of create the the vector sort of the that is needed for that query so that it can sort of run sort of a similarity search against our vector database and get the sort of similar sort of chunks from there. So here we've set like set it to three, like we'll find the top three chunks, and then you sort of like append that, like so you append this into a sort of results array list and then sort of return that so that you can append that to the actual sort of the LLM call that you do. So if you look at retrieve, ideally this should be in this part. So this is what our front end looks like. This is what I showed. So if you say ask question, so this is the ask question button. So if you press that, it's gonna trigger this the RAG query, right? So you've created this RAG pipeline object which has access to all the methods that we have, and you ask a question. So this is a question that we asked. So placeholder is what Python is used for. So you give a question, and you sort of extract that question and sort of run it through the RAG pipeline RAG query. So here, what it happens is like we'll give, let's say, the question we ask is like, what is Aquaflow? So it will go to RAG query, and it will sort of call retrieval system, which is this one. So retrieval system. So it will sort of call the retrieve method in the retrieval function class. So this one. What it does, as I told earlier, it will send the query, get the most common chunks, and you have now the context text, like what is the relevant information for this, and then you'll ask, okay, send a call to the generate answer method, which is the normal LLM call, right? So you have this here, and to that you'll have the query, which is the original question that you asked, and also the context, which was extracted from the vector database by sending it and getting the right kind of chunks. And so you'll have the general prompt here and the context that's coming from the chunks and the question, and you get an answer asking it to sort of have the answer here. And so we make a normal call to the LLM with this prompt that we created right now, and you get a response and you sort of return that, and that's sort of visualized on the UI side. So this is like how you normally sort of do a very simple RAG call. And yeah, I think we can do a lot more with it and do all these kind of re-ranking and things like that, but I'll go into detail in a bit what that means and how to evaluate this. Cool. Awesome. Um, so 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 this is like the way that you can simply build like a RAG solution, right? So the issue with RAG is like it is relatively probabilistic. You are sort of building like a probabilistic model, a probabilistic system, and things can change depending on the query that you give. And even the same query, if you give, there's more likely things could change, right? Because there's certain things that are sort of like moving parts here. So, so you want to make sure that you know how to evaluate how the RAG system works. And to do that, there are like different dimensions we can look at, right? There's retrieval metrics, right? So like some of the ways that you can draw these concepts from the normal search literature, where things like hit at k, which is like generally like figuring out like if it can retrieve like in the top k, like in the top k, does it have the right kind of information that is needed? So depending on like the chunks that you extracted, does it have the right kind of chunks that is needed to answer this question? So based on that, you can give a score. You can use another LLM to sort of score this, or you can get human evaluators to measure if what is get extracted is correct. And there's NDCG, normalized discounted cumulative gain, which is like a loaded word to say like to see if the order of chunks is correct, like the priority order, like is the number one in the list in the order is the most relevant document, is number two is the second relevant. So likewise, you can sort of look at these like re-ranked sort of the ranked order and figure out, okay, does it have the right kind of ranking, so that so you optimize to get these numbers scores high, right? And that's for retrieval part, right? So to make sure that the the vector database sort of provides the right kind of information for us, or any kind of like a knowledge system that you have, whether it gives the right kind of data from that end. But there's another angle to this, like the generation part. Like, can it sort of um, generate right answers? So you can do like exact match word to word, checking if the right kind of answers are generated. And there's another concept called ROG, which is another sort of measuring the n-gram overlap for recall and precision. So there are quite a few ways that you can measure rack systems, but it's important to know that you have like two parts that you need to measure. There's a retrieve part, and after you get the answer, you need to measure that if the answer is correct as well. So those are the two things that on a high level that you need to measure from a RAG performance point of view. Yeah, and sure, Bernard, yeah. Gotcha, gotcha. Yeah, that is true. Gotcha. Yeah, that's good feedback. Um, so yeah, so other parts is like this is like a bit more advanced stuff, but quite useful. Can get asked during interviews, but also quite useful when you build products. So like re-ranking, right? So like how do you sort of reorder candidates to um, after it get extracted? How do you sort of re-rank sort of chunks? So that's one sort of way that you can sort of improve this. And code expansion, right? So after you get a question asked, like does it have the right kind of is the question in the right format, right? So can you sort of make the user's question better? So you can sort of expand that and sort of paraphrase that so you can sort of the LLM would better understand that. So that's like another step that you can do, because if it has like human like sort of input at runtime, there's possibilities that folks can ask wrong questions, half-baked questions. So having this code expansion would help a lot better at sort of like runtime. To things like MMR, maximum marginal relevance. So it's another sort of angle that you can work on. Um, other things like guardrails. So generally you put these guardrails in place with any kind of AI tool, you do that, but also like RAG as well. So make sure that when there's uncertainty, you don't have to answer. For example, we saw that in this example, like when I asked like, what is Python? So it can't answer anything because there's no information in the context to answer this. It may answer right now, but let's see if it answers. So it doesn't have that information within the knowledge database to answer. So if the similarity matches is not strong enough, you can sort of block it off, saying, okay, there's not enough information to answer that question. So this is like a safe way that you can sort of safeguard your sort of AI tool, so that for it to only answer questions with what you already have. So it won't try to sort of like hallucinate things. So that's another way of sort of like safeguarding your sort of LLM tool. So yeah, I think like we sort of like we um discussed today like what RAG means, like why RAG is important, like about like different kinds of um um features of a RAG system that we can use to improve RAG, and the combinations as well, like re-ranking, how do you sort of do um bit of code expansion, and also like how you can sort of chunk these documents. I think that's the most important thing we discussed today. And how do you sort of protect your sort of LLM from like bad queries? I mean, we'll go into detail like how to add guardrails, but just know that you put these kind of like safety within your system so that you make sure that it gives the right kind of information and only answer question that it's supposed to. So these are the things we discussed today. And yeah, so we can get some questions in a bit, but like, so for this week's homework, I want to like ask you to like try and build like a very small RAG system, like pick any kind of a document set, like from a handbook, FAQ, blog. So, and see if you can split this into chunks based on a fixed size chunking or maybe semantic chunking. and sort of store this information in a local database like FICE, and see if you can sort of get some answers from them, and like make sure that you can measure the accuracy of these extractions, and see, and also experiment with like different types of chunking algorithms, right? So that to be fun, like to see what works and what is like good algorithm for you to test it out. Yeah, I think this is it for this week. And RAG is a yeah, it's a vast sort of field. I think the more you build stuff, more you experiment with it, like more you deploy these things in the wild, you'll sort of see the issues, you see like the things that work. So best to like, sort of get your hands dirty by building these things, and probably publishing so others can use it as well. So yeah, and this is what I want to cover this week about RAG and the concepts around RAG. Yeah, happy to take some questions. Got like 5 minutes, a couple of minutes left. Yeah, yeah, I mean, good feedback, man. So yeah, I think like how you can sort of evaluate like if you keep track of what's happening, like so you need to like figure out if the RAG is extracting. It's not just like LLM-based evaluation. Like you get like human evaluation as well to make sure that um, you get the right kind of information extracted and getting the questions answered as you expect it to behave. I think things like Langfuse we discussed last time, it's going to be quite helpful. So you can add Langfuse into the system so that you can keep track of like the questions that were asked, like, and the direct sort of workflow. Now you can figure out like what sort of chunking were used, and so based on that, like is the answer you got is correct. So yeah, it's quite useful. Yeah, I agree. I think like I mean, you can use S3 like any kind of database, like, and like Langfuse if you enable like the entire sort of to trace all of them, like you'll have that information. So definitely. So yeah, that's the most important thing about these LLM systems. You have to keep an eye out like how it's performing and like check and improve as you go. Yeah.